Very good morning to everyone. So here we are discussing the basic approach to the chemistry. So in the last classes we have discussed about the nature of matter, and in that classification of matter based on the physical, chemical and atoms, molecules, everything we have discussed. Apart from that, basic idea about the acids and bases. And in today's class we will discuss what is the acidity and basicity. Let us take a talk on acidity and basicity. So, what is the meaning of this acidity and basicity? Generally for acids we will take basicity, for bases we will take up this acidity. Generally acidity related to the basic compounds, it relates to bases, and basicity relates to acids. Then what it means, what is the acidity and what is the basicity? We will see here the definitions for these two. First let us go with the basicity. Basicity means it is the number of replaceable H plus ions by an acid. Means the acid how many H plus ions it can give. So that is called its basicity. Simply we can say like that, the number of replaceable H plus ions is the basicity of its acid. Let us take some examples here. Here the acid may replace one proton or two protons or three protons, so on. So depends on the number of protons replaced by an acid. We can further classify them as monobasic acids, dibasic acid, tribasic acid and so on, polybasic acid, like that. The first one, monobasic acid. Sometimes we can use another word also here, monoprotic acid, monobasic acid, or we can say monoprotic acid. Mean the number of protons replaceable. We can take few examples here. HCl, HNO3, acetic acid, formic acid, some etc. And these are the acids, so they can lose only one proton and the replaceable protons are one. So we can say these are the monobasic or monoprotic acids. We have the list, just remember some of these acids here. Next, dibasic acid. Or it is a diprotic acid. dibasic acid or diprotic acid. Means what? The acid which can replace 2 protons is a dibasic acid or diprotic acid. Examples for diprotic, anyone can give the examples here?
H2SO4, H2CO3, H2SO3.
We can take sulfuric acid, it can donate 2 protons, carbonic acid, oxalic acid. We can take, these are the few examples which comes under dibasic or diprotic acids. Very nice. Next, third one, triprotic acids or tribasic. Or triprotic. The acid which can replaces 3 protons, which can give 3 protons. What is the example in here?
H3po4.
We can take phosphoric acid, H3po4. Next, tetra, tetrabasic, or we can say tetraprotic acid. Simply we can say polyprotic instead, like this. Here this triprotic and tetraprotic, this mainly we can call polyprotic or polybasic. Usually more than 2, we can call them as a polybasic or polyprotic acid, which can give more than 2. Example for tetra basic acid or tetraprotic acid. CH4 is not an acid, it is a methane gas. Compound having the number of hydrogens may not equal to its protonic. 4 hydrogens are there, means we cannot say it is acid, and also we cannot say it can donate to 4 protons. I will take some examples, that also. So very important, that also. H4p2O7, very nice. Pyrophosphoric acid, H4p2O7. This is a tetrabasic. So very rarely they will ask you, better to remember this one also. So up to tribasic, mostly we will get in examinations. And I will give some other examples apart from this. Let us take some acids like this. H3po2, H3po3, H3po4. So H3po2, H3po3 and H3po4. Now tell me here, what is the basicity of these acids? H3po2 means hypophosphorus acid. The name of this compound is hypophosphorus. And H3po3 phosphorus acid. And H3po4 means phosphoric acid. This is the name of these compounds. Now tell me, what is the basicity of H3po2? Anyhow, here 3 hydrogens are there, and here also 3 hydrogens, and here also 3 hydrogens. Then is the basicity same for all these 3 acids or different? And if it is the case, what are the basicities? For H3po2, what is the basicity? Means how many protons it can replace, number of replaceable protons. It is a monobasic. So even though it has 3 hydrogens in we have only, it is a monobasic. It can replace only 1 proton. and H3po3 it can replace 2 protons, and H3po4 it can replace 3 protons. Then why it is? So that we can explain based on their structures. And here in case of H3po2, even though it has 3 hydrogens, the structure we can see like this, and out of these 3 hydrogens, 2 of the hydrogen directly linked to the phosphorus and 1 of the hydrogen directly linked to the oxygen. And whereas H3po3 structure is like this, and out of 3 hydrogens again, 2 of the hydrogens are directly attached to the oxygen and 1 of the oxygen directly attached to the phosphorus. And whereas in case of H3po4, the structure is like this, and here all 3 hydrogens they are attached to the oxygen. And we have the definition for the basicity. It is the number of replaceable H plus ions. Then which type of H plus ions can replace? The hydrogen which is directly attached to oxygen, only replaceable. And whereas the hydrogen directly attached to phosphorus, these are non-replaceable. And these 2 hydrogens are non-replaceable. Only hydrogen which is attached to the oxygen, only replaceable. So here in case of H3po2, we have only hydrogen that can replace. So we can say its basicity is 1. And whereas in case of H3po3, here 2 hydrogen they are attached to the oxygens. These 2 are replaceable again. And whereas this hydrogen is not replaceable. So we can say the basicity 2 here. Come to the phosphoric acid, and 3 hydrogen. These 3 hydrogens can replace. Why? Because they are directly attached to the oxygen. So hence its basicity is 3. So don't think that we have 3 hydrogens each case, so its basicity is equal to 3. So not, that is not correct. A structure is important, and what is the bonding of hydrogen is important. Understood on this one? This is very, very important. Any doubts here? Okay, then I will give one more example for the identification of basicity. H3po3, and this is a boric acid. H3po3 is the boric acid. Now again we have 3 hydrogens. Then what is the basicity of this boric acid?
1.
Here again, even though it has 3 hydrogens, again the basicity is 1. Again that is due to the structure. The boric acid is a trigonal planar structure, and one more important point on here, and these 3 hydrogens are directly attached to the oxygen. And just now previously we discussed that the hydrogen which is directly attached to the hydrogen is replaceable. But so according to that definition, these 3 hydrogens should be replaceable in nature. Means what? These 3 are replaceable means the basicity of this boric acid should be 3, but again it is 1. Why? Why? Because here none of the hydrogen is replaceable. Instead, and this boric acid is an electron deficient compound. Now here the central atom boron is surrounded by 6 electrons. The 6 electron means it is electron deficient. It is 2 more electrons lesser than the octet configuration. About this octet configuration, electron deficiency, we will discuss later in the chemical bonding. Till then just you remember. Okay. So 6 electrons means 2 more electrons less for the octet configuration, hence it is called electron deficient compound. Electron deficient nothing but, and which is having less electrons than the octet configuration. In the valency shell, it has less than 8 electrons. If it has 8 electrons in the valency shell, then we can say it satisfied the octet. Then that is electron precise molecules. If electrons are less than 8, then we can say electron deficient. So, in case of boron, we can see 6 electrons around the boron. So, electron deficient. So, in this electron deficient, so anyhow deficiency is there, so it cannot donate. If it has excess electron, then only it can donate, but there is no excess electrons here. So, here what happens, instead of donating or replacing this proton, and this boron accept OH minus from water. So, water we can split like OH minus and H plus. So, this OH minus, a pair of electrons can be accepted by this boron and it releases the proton from water. Since it is called acid, so it is a basicity is 1. But again one more point, we have used another terms there, monoprotic acid, diprotic acid, triprotic acid, tetraprotic acid, so on. And again here boric acid is not a protonic acid. Why? Because here even though it has 3 hydrogens, none of the hydrogen is replaceable, right. So, boric acid is not a protonic acid. This is also very important. Then what type of acid it is? Yesterday we have discussed generally electron deficient compounds or Lewis acids. The Lewis acid is not a protonic acid, and these 2 points are very important about boric acid. Again its basicity is 1 and the structure, electron deficiency, all these points you should remember, completely memory based and are also very important. Okay, this is about the basicity which relates to the acids. And the next one we will see acidity, that is related to the bases. Acidity. Just quite opposite to that one. So, in case of basicity, number of replaceable H plus ions, but here acidity means the number of replaceable OH minus ions. By a base. So, number of replaceable OH minus ions by a base in aqueous medium. So, how many number of OH minus a base can give? So, we can say that is its acidity. So, just like a previous a number of OH plus ions we classify like mono, di, tri. Here also we can say monoacidic base and diacidic base, triacidic base and so on. Okay. First one here, monoacidic base. Monoacidic base means what? The base which can replace one OH minus ions. We can take so many examples. So, what are the examples for monoacidic base known here? Sodium hydroxide and potassium hydroxide, rubidium hydroxide, generally first A group hydroxide you can take, etc. Ammonium hydroxide, some example, they comes under monoacidic bases. And the second one, diacidic base, which can replace two OH minus. Can you give some example here? Diacidic base?
CaOH taken once.
Yes. Calcium hydroxide, strontium hydroxide, barium hydroxide, some etc. This comes under diacidic bases. Next, tri. Which can replace 3 OH minus. Examples:
FeOH
aluminum hydroxide, ferric hydroxide, chromium hydroxide, we can take some examples. This comes under triacidic base, mostly mono, di, tri, enough. Tetra and poly not required here. So, this is about the base. There is no special exceptions as like acids case. In case of bases, direct examples only in case of acids, the basicity, especially phosphorus acids and boric acid, that you should remember, that is very important. If I take one more compound like this, what is the basicity of this compound? BOH taken thrice. Again it looks like the triacidic base, but first of all it is not a base. What is this compound, Anna? BOH taken thrice? It is a boric acid only. Okay, we can write the formula boric acid like this, or BOH3 twice. This is also very important. Why? Because representation of boric acid is very important. Having OH means it's not a base. That is why it cannot donate H plus ions individually. Okay, anyhow, this is something some basic idea about the acid base. Anyhow, we have discussed in the last class, and acidity and basicity. Next, one more important point here. This is also memory based experimental analysis. They will ask you sometimes which is a stronger acid and which is a weaker acid, which is a stronger base and which is a weaker base, that kind. We will take a few examples here. Why? Because mostly we will use these examples. We should know what is a strong acid. Just I will go with the example according to experimental analysis. Strong acid. So, if we define according to Arrhenius, we can say that which can give H plus ions effectively, means 100% H plus ions releases, 100% of ionization. That is a strong acid. Or if we say according to Bronsted, the strong acid definition, we can define like this. According to Bronsted, what is the acid which can donate H plus? So, here tendency of H plus is more, then we can say it is a strong acid, and tendency of donating H plus is less, then we can say it is a weak acid. Same like according to Lewis, the substance which is having more tendency to accept a pair of electrons, strong acid, and less tendency to accept a pair of electrons, weak acid. So, quite oppositely we can give the definition for bases, strong base, weak base, again which can give OH minus effectively in aqueous solutions, I mean 100% ionization is a strong base. According to Bronsted, the tendency to accept H plus ions is more, then we can say strong base, and also tendency to donate lone pair is more, so strong base. Just according to their releasing of H plus ions, accepting of proton or donating of proton, whatever it is. But that we cannot say theoretically, that is experimental phenomenon. Just we will go with the example. Strong acids, we can take some of the strong acids like this, HCl. Why? Because we will use sometimes what is a strong acid, what is a weak acid. HNO3, H2SO4, HBr, HI, HClO4, some etc. This comes under strong acids. And weak acids, among hydrogen halide, there is a halogens, HF comes under weak acid. And all phosphorus acids, H3po2, H3po3, H3po4, they comes under weaker acids. And apart from this, mostly organic acids, carbonic acid, and organic acids, acetic acid, almost all organic acids, they comes under weak acids. Comparatively only, compared to this acid, they are little weaker. Formic acid, oxalic acid, all these acids we will use frequently. So whatever the acids we will use further, that only I am writing here, I am not writing all. Hydrogen cyanide, some etc. And these are the weaker acids, just remember. Again, one more important point, among the phosphorus acids, the acidic strength, again this is also one exception. H3po2 is a stronger acid than H3po3. So among them comparatively, H3po4, and this is also you should remember. Strong acid, weak acid, examples. And the next strong and weaker acids, we have the strong base and weak bases, that also we will take up here. First, strong base. Mostly metal hydroxides, that is a S block metal hydroxide, first A, second A. You can take sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and calcium hydroxide, strontium hydroxide, barium hydroxide, etc. This comes under stronger bases. And weak bases, among all weak bases, mostly we will use this one, ammonium hydroxide, we will use regularly, and this is a weak base. Apart from this, you can go with magnesium hydroxide, some other aluminum hydroxide, ferric hydroxide, etc. This comes under weaker acids, weaker bases. So just memory based, you should remember these things. This is about acidity and basicity. First of all, any doubts up to here? Tell me, Nana. Any doubts up to this? All of you following? Yes.
Sir, what is the definition of strong acid and strong base, weak acid, weak base, sir?
With respect to, we have three theories. No, with respect to three theories, we can define. Let us take Arrhenius, for example. We will take up strong, which can undergo 100% ionization. So, which can give a complete H plus ions. The acid which can undergo complete ionization. What is this complete ionization? We will discuss later. Means it will give, for example, if I take HCl, 1 mole HCl if I take. So, if you add to the aqueous medium, it should give 1 mole H plus, 100% of H plus ions it should produce. Then the type of acid we can say stronger acid, which can give 100% of H plus ions. And if it is 90%, only 80%, 50% only ionization, then we can say it is a weaker acid. That we cannot say here theoretically, that is experiment, which can give 100% means they will calculate. Understood? That is according to Arrhenius. Similarly, same base also, the base which can produce OH minus 100%. For example, if you take NaOH, you add to the water, you can see complete formation of Na plus and OH minus, completely undergo ionization. Now we can say sodium hydroxide is a stronger base and HCl is a stronger acid. That is according to the Arrhenius, we can define like that, or according to Bronsted. Bronsted-Lowry. According to Bronsted, what is the acid first of all which donate proton? It is a tendency to donate proton is more. The substance which can donate proton effectively, that substance we can say stronger acid, like HCl. In case of HCl here it can donate H plus 100%, it can give complete H plus, it can transfer H plus 100%. So more, tendency to donate H plus ion more is called stronger acid. Quite opposite, which can accept H plus very effectively, that we can say Bronsted base. Similarly, Lewis. So according to Lewis, there is a tendency to accept a pair of electrons or tendency to donate. Tendency to donate electron pair. If a substance donate effectively the electron pair, we can say it is a stronger base, or accept electron pair effectively, we can say stronger acid. That's it. Understood?
Yes, sir. Thank you.
Next, one more important with respect to chemical reactions, how to identify the acidity and basicity. This also will give some basic idea. Let me take one reaction like this. Generally, acid base reactions, they can undergo neutralization and they will form salt. Instead of H3po4, let me take HCl. If we treat with sodium hydroxide, what happens here? The neutralization reaction, salt formation. It will form NaCl and H2, salt and water formation. Let me take one more example. H2SO4, if I treat with NaOH, I will get sodium sulfate plus water. If I take here 2 moles, but if I take same H2SO4 and 1 mole of NaOH, then in this case I will get sodium bisulfate plus water. Now come back now, the acidity and basicity. If I ask what is the acidity for HCl and what is the acidity for H2SO4 in this case, and what is the acidity of H2SO4 in this particular reaction. Anyhow, according to our definition, HCl, acidity is 1, basicity is 1 here for HCl. And H2SO4, what is the basicity of H2SO4 in this particular reaction? 2. Again, if I ask what is the basicity of H2SO4 in this particular reaction? So even though it is a sulfuric acid, but in this particular reaction, the basicity is 1 only, not 2. Why? Why? Because according to the definition, basicity means the number of replaceable H plus ions. Now if you see here, H2SO4, it replaces only one H plus, one hydrogen replaced by the sodium here, even though it has 2 hydrogens, but in this particular reaction number of protons replaced is 1 only. So we can say it is a mono, it can act as a like of monobasic. In general statement, what is the acidity, what is the basicity of H2SO4 means, we can say 2. but with condition, with some giving some reactions. If they ask what is the basicity, means you have to see how many protons are replaced in that particular reaction, that is its basicity. Understood this? I will give one more example here. Let me take H3po2 and if we treat with NaOH, we will get NaH2po2. This compound name also very important, you should remember. It is a sodium hypophosphite. And the same H3po3, if we treat with NaOH, we will get NaH2po3. H3po4, and if we treat with NaOH, we will get Na2HPO4. Again, these are a kind of acid base reactions, neutralization reactions. In this case, if I ask what is the basicity of phosphorus, hypophosphorus acid and phosphorus acid and phosphoric acid, and the first case, in the first reaction, tell me H3po2 basicity, how much it is? One only. Second case on H3po3, if we treat with NaOH, what is the basicity of H3po3 here? In this particular reaction, basicity of H3po3. Two. Just recollect previous example. Just to recollect the previous example. This one. One here. Just you check, Nana. H3po3. How many protons replaced? So you are getting H2po3 here. So out of 3 hydrogens, only 1 hydrogen is replaced. So we can say here is 1. Now in the third example, phosphoric acid basicity. Here, see here, out of 3 hydrogens, 2 hydrogens are replaced by the sodium, only 1 hydrogen left. So here 3. Sorry, 2. I only gave wrong. This is 2. Out of 3 hydrogens, 2 are replaced. Understood. The same we can give for the bases also. For example, if we take HCl, if we treat HCl with the calcium hydroxide, for example, we are getting here COHCl plus H2. If this is the case, what is the acidity of calcium hydroxide here? Generally, if they ask what is the calcium hydroxide, acidity means 2. But in this particular reaction, only 1 OH is replaced. So 1. So like that, we have to check for both acids and bases. Understood this one? A general definition is different, but exactly in a chemical reaction, that is different. Now I will give some questions. Just tell me the answers for this. See this particular question. Just from our previous discussion from nature of matter, acid, bases and atomicity and everything. Which statement best explains the fact that gases can be compressed? So, what is the answer in this case? Option A is given: particles in a gas do not have fixed volume. The particles in a gas are very far apart. The particles in a gas have no force of attraction between them, and the particles in a gas are constantly moving very rapidly. What is the answer for this?
B.
Option B here. Very nice. So, compressible in nature means they are far away. So, you can compress them to bring close to each other. Very good. See this question. In a solid, particles are packed closely together. There are strong forces of attraction between particles. Particles vibrate about their fixed positions, and all are correct. A na D na? D only. So, all are characteristic properties for the solid only, isn't it, Nana? The gases hydrogen, oxygen, nitrogen are considered to be: are they elements, compounds, atoms or mixtures? Elements or atoms? Elements. And see this question. What is the atomicity of argon? One. Is all noble gases are monoatomic in state. And this also you can do very easily based on atomicity only. 6 or 7? 6. What? 2 hydrogens, 1 carbon, 3 oxygens. C option. And I'll ask you one more question here. What is the atomicity of blue vitriol? You should know what is the blue vitriol. Find out, tell me. What is the blue vitriol first of all? Any idea about the compound blue vitriol? Crystalline copper salt. Okay, chemical formula, tell me. Cu
CuSO4 into 5H2O.
dot 5H2. So this is a blue vitriol. Okay. Now once if you know the formula, you can. So means here formula identification also very important. Why? Because sometimes they will use some commercial names, and based on the commercial names they will ask you the questions. So then we have good in that also. Now we can calculate that one. 21. This is 15 and 621. And if I ask one more, Morse salt, Nana?
39.
I think here's a few of the people already listened the classes, right? They rejoined. Morse salt, what is the chemical formula? Is a ferrous ammonium sulfate. FeSO4, NH4 taken twice, SO4, 6H2. Or you can write this also like this, the formula. NH4 taken twice, S4, and FeSO4, 6H2. Just double salts only. So how much you are getting? 31. Eh? SO4 taken twice. Where, Nana? No. Iron plus 2 sulfur, SO2 plus 2, minus 2. 31 we are getting. 39, huh? 31. Just you check, this is 18 and 5, 23, and this is 10, 33 and 5, 38, 39. Okay. So like this, some questions can be asked. See this question. Oh, so here sulfur dioxide is a acidic oxide. When you dissolve in water, you will get acidic solution. Very nice.